Welcome to the Course One podcast. In this podcast, we explore the emerging open financial system. We dive into scalability, interoperability, proof-of-stake, blockchains, and many other parts of this coming financial singularity. Tune in every Monday to dive deep into these cutting-edge projects and protocols with Course One team members and guests.
Hi, and welcome to the Chorus One podcast. Today, I'm joined by Shirley, CTO of Dapper Labs, building the Flow blockchain. Hi, Dieter. Welcome to the podcast.
Hey, how you doing, Felix? It's a pleasure to be here.
Awesome. Great to have you here. I think there's an interesting background for how you came into the crypto space and your journey through it. So why don't we start with that? Why don't you start telling us a bit about your background in crypto and how you joined the Dapper Labs team and what you've been doing so far?
Yes, well, I got into Bitcoin a very long time ago. I actually mined my first Bitcoin on a CPU miner. We didn't even have GPU mining software at that time. And I thought it was really cool technology. I have always lived in Canada, and so I'm less skeptical of the government than most, I think. But I just thought the technology was really cool. It was a really neat application of cryptography and of decentralized systems, and I got really excited about it early on. But I didn't put any sort of professional effort into it. And then in 2013, I joined a company called Axiom Zen, and of course, everyone was very excited about Bitcoin at that time as well. And so I sort of rekindled the interest in it. And the Axiom Zen team actually started exploring what it would look like to get into decentralized technology. And we sort of decided it was a little bit early. And so we continued on building other products. And Axiom Zen is a really interesting company. It's been around for a while, so we no longer call it a startup, but we used to refer to ourselves as the startup that builds startups. And we've actually had multiple companies spin out of Axiom Zen. There's Zen Hub, which is a project management tool built into GitHub. There's Routify, which is routing as a service used by multiple companies, and so we're always looking for the next wave. And so when 2017 came around and everyone was getting really excited about blockchain again, we really started looking hard at it. And we spent a bunch of time looking at a bunch of different projects. We had, at one point in time, we had a list of 16 projects that we were like, this could work, right? And it was everything from, like mining, like literally digging things out of the ground and building marketplaces, decentralized marketplaces for mining services. We looked into real estate. We had looked into, sort of almost like matchmaking, the generic matchmaking problem, which, it applies both to dating and to job hunting, right? But in the end, we said, well, let's just start with something light. Let's just start with something easy that it teaches our team something about how this technology works. It's fun. If this thing all goes bust, we're not gonna put a bunch of company effort behind it and lose a lot of progress that we could be using to work on other projects. But, And even if people look at it, they'll always get a smile. At least they'll smile about it, right? And that was the Cryptokitties idea. So that was one of our 17 ideas. And the origin of that was literally just my coworker Mac coming to me one day and saying, "We're going to put cats on the blockchain." And I said, "What does that mean?" And he said, "I don't know yet." And so we decided to give it a try. And so it was just a 4 months from conception to delivery, 3 months of actual engineering effort. And it was just intended to be this fun, engaging thing that embodied the best of decentralization in a way that normal folks could understand. The people who weren't necessarily technical could appreciate. And of course, it hit a perfect storm of when it hit. Everyone was, very excited about it, about blockchains in general. And Cryptokitties came out, and it was one of those things where people who were into crypto really had been telling their friends about it for months and months, finally felt like they had something that would make sense to these other people. And so, of course, it exploded. It was at one point in time using somewhere between a quarter and a third of all the gas on the Ethereum blockchain. And of course, that pushed Ethereum over the edge, right? It had been running over half capacity before we came along, and we just really pushed it over the edge, and Ethereum burnt down. And the thing that blew me away is that as exciting as it was, as many people that came and actually checked out Cryptokitties, the number of people who were actually interacting with our smart contract on chain was relatively small. It was somewhere between 10 and 20,000 people were daily using our smart contract. And yet we were hitting the limits of Ethereum. And one thing you could say is that, well, you're sharing the blockchain with other people, but even if we had Ethereum to ourselves, we would have had maybe 3 or 4 times as much capacity. That's not enough to have a consumer product. That's not enough to have widespread, mass market adoption. And so, after the craziest died down, this is January, February of 2018, and sort of everything sort of was settling down, we asked ourselves, okay, well, this is very exciting. Like, we've obviously found something interesting here. The consumers can care about this stuff. It's not just this weird nerdy thing. It's not just this financial thing. There's something fundamentally interesting about digital assets that you own that doesn't have to be financial in nature. They can be personal. They can be fun. They can be entertaining. And so, obviously at the same time, we're talking to investors, and Andreessen Horowitz and USV led around our first round of investment that closed later that spring. But we were also asking ourselves, well, if we're going to go after a consumer market, how the heck are we going to do this on the Ethereum blockchain? And so we can't, right? Like, we need something. We need a layer 2 scaling solution. We need a different layer 1 chain. And so we started doing investigations, and we talked to everybody, right? We talked to Cosmos, we talked to Solana, we talked to Definity, we talked to, who else was active in those days? A bunch that sort of haven't gone anywhere since then. But, we read, 20, 40, 50, I don't know what it was, white papers. We talked to over a dozen teams. And in the end, we realized that more or less you could divide almost every scaling solution into 2 sort of buckets, right? One was people that were really limiting participation, right? And you put sort of Tron and EOS in that bucket. And they were sort of saying, look, like, we can only have so many people who are participating in this thing because everyone needs to do every computation. And if you want to have high throughput, that means that everyone who's participating has to have a data center scale computation power. And so we're just not going to be able to have lots of those people. So let's just have a small number of people that all are data center scale, and that's decentralized enough. That was sort of a phrase that lots of people were talking about in 2018. And we didn't like that. We felt that sort of natural market pressures, things, natural economies of scale are always going to have centralization pressures on these systems. And so if we didn't build the protocol to have maximal decentralization pressure, that eventually is the centralization pressure and the cartel and cabal formation was going to reduce the number of participants. I mean, we even see this in Bitcoin and Ethereum, where mining pools have such economies of scale that they've just basically represent the vast majority of the hash power. And so we didn't like that solution. So the other option was to do sharding, and we put something like Cosmos and Polkadot, now Polkadot didn't really exist at that time, in that same sort of world of sharding, because obviously it's not sharding. What Cosmos is doing, his vision is very different than a sharded blockchain from Ethereum 2. But our concerns about sharding are the same as concerns as we had in Cosmos, which is one of the things that we thought was so interesting about Cryptokitties was that you could have smart contracts talking to smart contracts, right? Cryptokitties is 3 different smart contracts deployed to 3 different addresses. And soon after we launched, a team put together something called Kitty Hats, which is one of my favorite projects of all time, which allowed you to dress up your cats. You could buy sneakers, sunglasses, and obviously hats for your cats. And their smart contract depended on ours. Their smart contract was an extension of ours, but we couldn't block it. We couldn't prevent it in any way. We couldn't slow down their growth. But at the same time, because what we had published was a secure smart contract, they couldn't undermine our product either. And so we had this like amazing synergy where they could create something that if users thought it was valuable, was a pure value add for our users, but couldn't possibly undermine the sanctity of the smart contracts that we had already created. And if users didn't care about dressing up their cats, they didn't need to be bothered by this. And so, in the game community, we call this modding. In other software contexts, we call them plugins, extensibility. The phrase that people have used in the blockchain space is composability, right? And we didn't have that word, but we knew that different people building different smart contracts and having those smart contracts work together was really, really valuable. And we were concerned that having asynchronous communication between smart contracts, which is what sharding requires, which is what a hub and spoke model like Cosmos requires, and was going to limit the number of interactions that they could have, right? So if I want to send tokens from one contract to another, that's no problem. If, however, I want to do something more complex, I want to do an exchange. I want to do like a three-way exchange where, Sally gives something to Bob, and Bob gives something to Charlie, and Charlie gives something to Sally, and we want it to be an all or nothing. It's very hard to do that asynchronously without allowed a lot of locking, and locking is complex and it's error prone, and it can cause all sorts of issues. And so we didn't want to have to pick either of those paths, and so we locked ourselves in a room. It was two engineers, a product manager, and me. I don't know why I don't count myself as an engineer. Three of us engineers and a product manager. And we locked ourselves in a room, and we said, well, does it have to be this way? Like, is it just given that you either limit participation or you have all of these different separate state domains that interact asynchronously? Do we just need to live in one of those two worlds, or is there another way? And so we started by asking, well, how do other systems scale? And so we looked at CPU design and the way that software or instructions are pipelined through a CPU, and we said, well, what does pipelining do? What if we break the process of doing what a blockchain does into a bunch of different steps? And I think I can't remember the exact number. It was like 11 steps or 13 steps, something like that we said, each of those steps could be sort of thought of independently. And what we realized is that you could, I suppose you could have like 13 different nodes, each doing one of those steps, but then suddenly the network efficiency and the latency gets really high. But we realized that if we could group them into, ultimately 4 groups that we settled on of operations that needed to be done, that we could create a system where we could choose what part of the, this sort of Vlad's triangle or the scalability trilemma, each of those node types could be at a different point in that triangle, so that the system overall, so each part of that system, of course, followed that, trade-off between scalability, decentralization, and security, but that each node type had to have one point in that triangle, but the system as a whole didn't have to pick one point, because we could do that balancing, those trade-offs for differently in each different node type. And so the 4 node types we ended up with were collectors, consensus, collection, consensus, execution, and validation. And having each of those separately, we could have a different trade-off for each of those. And so that's how we were able to not compromise on security and decentralization, but still have high scaling throughput. Okay,
wow, that was really, really nice monologue here. He took a lot of my questions already away from me, but that was really nice. I think that gave an amazing background to people that aren't so familiar with these problems. Maybe something before we go again more into these 4 node types, which I think is probably one of the most interesting design pieces in Flow. I wanted to talk a bit about the traction that you experienced with Cryptokitties, and then the decision to focus on this gaming use case. I think Flow also, just seeing the investors and you also still building these games, there seems to be this focus on the entertainment or let's say games, virtual worlds use case. But now we are obviously also seeing this composability being very useful in these financial applications and in these kind of decentralized finance applications. So just a few days ago, I guess, we run it again into some peak gas usage based because of oracles and liquidations happening on Ethereum because of the price drop. Do you think Flow is also set up for these use cases, or is it more generalizable to these use cases, or is it really we're focusing on this virtual worlds stuff?
So our goal was always to bring decentralized technology to a consumer audience. And our thesis was that most consumers were not going to be overly concerned about the financial use cases, or at the very least, they would in their minds to some degree separate the financial use cases from the entertainment use cases. But which isn't to say that we don't think that other stuff is interesting, and that those other ideas of and remember I said before we decided to build Cryptokitties, we were looking at insurance, we were looking at real estate, we were looking at decentralized markets for off-chain services, but the thing is that people aren't going to. We didn't think that most people were going to learn that stuff and by reading blog posts, by having their buddy explain it to them over coffee, right? No one wants to be that Bitcoin guy. But this technology is so exciting. We all end up being that Bitcoin guy sometimes. But the point is that we felt that if we could create use cases where the ownership was real, where the facilities that people had were not mediated by some central corporation, that it wouldn't take them very long to say, well, wait a minute, how come I have more power, freedom, and autonomy with my Cryptokitties than I do with my insurance, my mortgage, and my bank account, right? And that's what would bring them over. And so our goal was always to say, look, we're a consumer-facing company, but that doesn't mean we stop with games and entertainment. That's what we start with. And so our goal was to do all sorts of consumer applications in the long run, but we felt that we were never going to get people to trust their mortgage to us, their insurance to us, until they understood, in sort of in a visceral sense, not by reading blog posts, but just by using it, what this technology meant, right? I think that, I've been in this industry long enough to remember trying to explain the internet to people, and explaining the internet people never worked, right? Letting them use email, letting them see a web browser, that's what worked. That's what got people excited about the internet. And everyone today understands the importance of the internet. But most people still can't tell you how packets get routed, right? And the way we got people comfortable with and interested in the internet was not by explaining packets to them over and over again. It was by showing them things that actually had value and utility to them. Those were things like Facebook and Twitter and email, right, was sort of the first big one. And so that's a really, really long-winded way of saying that when we started building Flow, we wanted it for entertainment and gaming use cases. But we never, ever wanted to limit it to that. And in fact, the way we thought about it was that if you can do gaming and entertainment, you can do all the other stuff. But that wasn't going to be our focus. That wasn't going to be our message to people, to consumers. With that said, I genuinely feel like Flow is probably going to be an excellent blockchain for DeFi use cases. You have we have lots of facilities built into the blockchain that make a lot of the DeFi facilities, easier to understand, easier to keep track of, less code to do, more interesting and complex things. And I assume I don't want to steal more of your questions, but we're even rethinking how the programming language works to make sure that composability is sort of built right into the language and isn't just a construct where smart contract is talking to other smart contracts. That you can actually mix data structures defined by different smart contracts together safely, and while still guaranteeing all of the rules defined by those smart contracts. So Flow is the blockchain that we want to build on, and we think that most app developers will want to build on, whether they're interested in entertainment use cases or sort of the stuff that's more traditionally been associated with blockchains.
Okay, good. Yeah, as you said, I think that's really interesting to see it coming from this. Also, you probably writing these apps yourself and seeing where the problems are, right? And obviously, consumer applications seem to be a good first step to that. So maybe we can talk a bit about how that went. I guess, do you think it helped you to build these Cryptokitties on Solidity to inform you the choice to make a new programming language? Or do you see other people also coming to the same conclusions that maybe didn't have this experience?
I think our experience building in Solidity, building on Ethereum, has informed so many micro decisions about how flow works, right? So there's some macro stuff, right? The big ones, the scaling issue and things like that. And I think a lot of positive things, right? Like, the thing that we keep from Ethereum that is so valuable to us is that, uncharted state where every smart contract can synchronously interface with every other smart contract. That is incredibly valuable, and we saw it and leveraged it directly in our smart contracts that we delivered, and then we saw other people building on top of our smart contracts, building all sorts of cool stuff, beyond kitty hats, right? There's kitty racing, there's wrapped kitties, which is an ERC20 version of Cryptokitties, which is hilarious because Cryptokitties were, definitionally non-fungible, and then someone's like, yeah, but what if we made them fungible? And like people can, people have the power to do this because it's all sort of one shared state. But just so many things about, and just give you one example, right? So one of the things you need if you're going to deliver a smart contract development platform is you need a way for people to write their smart contract and test it, right? No one's going to upload a smart contract that's never been tested to the mainnet. And even uploading to the testnet, you want to have done some amount of local testing before you go to all that trouble to put it on a public network. And, the truffle tools from Consensus are what we used for Cryptokitties, what we used for Cheese Wizards. And, thank God they exist, because going directly to the testnet would have been even more painful. But because it, is based around this local copy of the blockchain that is, more or less spins up an entire copy of the blockchain. It takes several seconds to launch it. The interaction patterns between uploading, sort of submitting the transaction and letting the block get quote unquote mined locally, obviously it's much faster than a test network or a main network, but it's still slow compared to traditional software development, right? It's still slow compared to, sitting inside, whether it's Xcode or other IDE, and just, making a change to your code and hitting run and just having it, sort of instantly respond. And so one of the things we did early on was we said, look, there's got to be something that is different than the testnet, that is different than, running a little copy of the blockchain locally. There's got to be, we call it the emulator. And what it is it's a process that can spin up in less than a second, and you can start submitting contracts and transactions to it, and it responds very, very quickly. It's got an interactive command line to it. And so you can interactively, test your smart contract instead of just doing it sort of this batch processing. And that's really powerful. And that comes directly from the experience that the team and I had working on those smart contracts in Solidity, where it's like, oh, that's my bug. One character fix, then wait 10 seconds for, your testing to find the next one character bug, which, all developers make. And so being able to have a much faster interaction pattern there is, we're already seeing it, right? Our team is building smart contracts for our own stuff, and they're already talking about how much more productive they feel working inside this environment. And that's not a feature necessarily that you put on your blockchain, development page, or that investors understand, but as people who've gone through the pain of what it means to actually build production code and ship it, we had a lot of insight there, and that's just one example. I mean, there's so many other little things, that we could not possibly have understood if we hadn't done so much development on Ethereum.
That's really cool. I mean, do you think this type of emulator, which is also another cool gaming reference, I guess, I don't know where this name is coming from, but that's how I know it. Is this also possible to build for Ethereum, or does this also exist now on Ethereum, or do people still use Truffle mostly, or would this even be possible?
Well, I mean, technically, I suppose Ganache which is the heart of Truffle, is an emulator, but because it was built after the fact, and because so much of how Truffle is structured is based on modifying I believe it's Geth. It could be Parity. I don't actually know. But modifying the existing node software rather than, building a whole new version, there's only so much that you can sort of safely take out, right? Because all of those things were built with the mindset of like, hey, we're on a network. We have to, check all of this stuff. You can't sort of short circuit that. Whereas if you were building, Ganache at the same time as Geth, right? Then you would say, oh, well, we're going to reuse this component, but we're not going to use that component. And so that reusable piece can't assume the existence of that other piece. And so it's a lot of little micro decisions that roll into it, but it means that we're more thoughtful about how we're separating our code into modules, which modules will be used in the emulators, which modules we don't need to use in the emulator, right? We don't need to run consensus inside our emulator. And so, we're able to do some things. We don't need to do, for example, state proofs, right? We don't need to build all these big Merkle trees, which is actually one of the most expensive parts of processing an Ethereum block. So that's where it's just having that mindset from begin with. And could you build something like that for Ethereum? Absolutely, 100%, no problem. Problem, right? It would be a lot of work, right? And that's the issue, right? Is that how much work are you going to do to build all the same stuff over again, just so you have a faster developer experience? Whereas if we are doing it while we're building the first version, we can actually, it's a very small delta for us to just keep that in mind as we're building.
Okay. Yeah. Speaking of separation, I think maybe we can go back to the separation of the nodes. I guess this is like another insight that you already mentioned and explained how you kind of got through this decision to maximize participation while at the same time keeping security and scalability. So maybe can you again mention the 4 different node types that Flow has now, and maybe kind of talk a bit about how these differ, what each of these nodes is doing?
Yeah, for sure. So the easiest way to understand how the nodes work is just to follow the path of a transaction. And so what happens, right? I am a user. I'm using some dApp or other client software, and I want to submit a transaction to the blockchain. So what happens, right? So that transaction gets submitted to a collector node. So the collector nodes, what is the job of the collector nodes? Well, the primary job of the collector nodes is, well, as the name implies, is to collect the transactions together and to send a commitment to a bundle of transactions to the consensus nodes, rather than sending a copy of all the transactions to the consensus nodes. So one of the things that is really important to understand is that one of the reasons why scaling is hard in blockchains is because networks are slow. And getting a copy of all the transactions to all of the nodes is actually a really hard problem. And so one of the things we decided early on is that the consensus nodes we should work as hard as we can to limit the amount of network traffic that the consensus nodes need to engage in. And so what the collector nodes do is they build these things called collections, which consist of, let's say, 1,000 transactions. And then they create a single commitment, which is a hash and a set of signatures that go to the consensus nodes. And they're saying, look, we've got a block of transactions here. And if this isn't a valid block of transactions, we'll get slashed later. And if it is a valid block of transactions, we'll get paid. And so that's why the collectors are doing their job, and that's why they're doing an honest version of that job. So they collect the transactions together, they build a collection commitment, and they pass that commitment on to the consensus nodes. The consensus nodes then take a group of commitments from a variety of different collectors, and they build a block. And so if you imagine that each collection is, maybe 1,000 transactions, then, if they have 10, they could just have 10 commitments, right? A commitment is no bigger than a transaction. They can have 10 commitments. They could have 100 commitments. You could even imagine them having 1,000 commitments in a reasonably sized block. And so they can undergo a standard BFT consensus algorithm with on these commitments rather than on the transaction text themselves. Now, one thing you might ask yourself is, well, how do they know that the transactions will succeed? How do they know that these transactions are even well-formed, et cetera, et cetera? That's a job that the collectors have to do. They have to make sure that at least the payer, right, the person who's paying to pay for that transaction, has enough money to pay for that. Otherwise, they'll be on the hook for it, right? So we just basically say, you figure out whether or not they have enough money. If they don't, you'll pay for that transaction. And so once we know that the transaction can be paid for either by the person who submitted the transaction or by the collector, then there's zero risk in including a transaction, right? We have transactions in Ethereum all the time that fail. We don't have to know that the transaction is going to succeed. We just have to know that whether or not it succeeds or fails, someone's going to pay for it. So now the consensus nodes can take these commitments, they can build a block, and that block can be very small, right? A 1 or 4 megabyte block could contain, hundreds, if not thousands of these commitments. And so they engage in a BFT consensus. We chose hot stuff. It's more or less a pipeline version of Tendermint. So it's the same basic algorithm as Tendermint, but it's pipelined in and of itself, where the pre-commitment is also for one block is also a pre-vote for the previous block, which is also a commitment for the block before that, right? And so they sort of bundle these things together, and so you get a little bit of efficiency gain there. So once a block is finalized, that block then goes to the execution nodes. And so the execution nodes, what do they have? Well, they have a block that is finalized, right? Like it is finalized in the way that a Cosmos block is finalized, right? This thing can never change. We don't yet know what the output of all the transactions in this block are, but what transactions are included, what order they should be executed in is known. And so the output of that block is more or less deterministic, right? There's one caveat there that I'll get to in a minute, but barring this caveat, the output of that block is actually entirely deterministic. And so then the execution nodes go to the collectors and say, hey, I'm about to process this block. It's got these collections in it. You made a commitment to these collections. Either give me the data in that collection, or I will initiate a slash on you. And so that's the sort of the one caveat there is that there's still this chance that a collection will go missing, and so there is still this chance that the output of the block might change somewhat. But we think that collections will go missing with a very, very low frequency because it's not a very interesting attack, right? And it's not a single collector that's making a commitment to a collection. We group the collectors into clusters, and it has to be everyone who signed that collection, and multiple people, 10, 20, 30 nodes have made collection nodes have made a commitment to this collection. And so if they all go offline, then the collection can go away. So that happening accidentally is very unlikely. And in an intentional attack, all that ends up happening is you get slashed and those transactions aren't included in the block because we can still execute everything else in that block. And so it slows the network down while we resolve whether or not this collection is actually missing. But it's not a very interesting attack other than slowing down the network. So the execution nodes, they get all the collections. That includes all of the transactions. And these execution nodes are very powerful. We're imagining, multiple servers living in the same data center, a rack of high-powered SSDs, enough RAM to keep, the entire Merkle tree for a very large state set in memory. So you're not doing all of these seeks that slow down, the Merkle proofs in other contexts. And so it can have a very, very high throughput, and it itself can have a very pipeline thing where you're like, first you're loading up the state, then you're executing the state, then you're generating all of these, the after the statement commitments that come after. And each of those can be happening on not just a different CPU, but potentially a different server with its own memory pool. And so at the end of that, the execution nodes come up with a result. And, I'll stop talking about the missing collection case for a second because we do think it's very rare. If people are interested in that, I encourage them to go and read our technical papers. We go into great length in how we handle that missing collection case. So it is handled, but we'll assume the case where the collections are all there. And so all the execution nodes should come to the same result. Every computation is fully deterministic. It has to be, that's the nature of how verifiable blockchain computations work. And so every execution node should come to the exact same result. And if the execution nodes don't come to the same result, we know that somebody's lying, right? Maybe both of them, but we know at least somebody is lying. And so the question then becomes, well, how do we know who's lying? And how do we know that not everybody is lying, right? What if all the execution nodes are colluding and producing an invalid result? How do we know that that's not happening? And that's where the verifiers come along. There is this neat property of linear calculations where even if the calculation is fully linear, meaning that you have to calculate the output of transaction 1 in order to even begin computing transaction 2. Because transaction 1 may or may not send money to this person, and transaction 2 therefore may or may not have the money it needs to send to the third person, and transaction 3 and so on, right? So we have these linear transactions. We know that if we're having a shared state, that we have to execute them linearly. Even though we have a fully linear execution path, you can verify them in parallel. Actually, Vitalik did his presentation at DevCon in Osaka last year was actually on this exact topic. And I can't remember the word he used for it, but it was really neat to see him talking about it because it was a concept that we'd been depending on for over a year at that point in time. And he was explaining it in another context. But when you have this fully linearized thing, what you do is you just do these checkpoints and you just say, look, the path from transaction 1 to transaction 100, it results in this state root, right? Here's a state commitment after transaction 100. And then if you execute transactions 100 through 200, you end up with this new state commitment, right? So we'll do that simple case where there's just two of these chunks, right? With these two with one interim commitment, and then you have a starting commitment and an ending commitment. And you go to verifier A and you say, hey, I want you to check that the transition from the starting state through the first 100 transactions results in this interim state. And you go to verifier B and you say, assuming this interim state is correct, do you actually get to the final state after transactions 100 through 200? And so we don't know if verifier B comes back and says, yeah, the transition from the interim state to the final state is accurate, 100%. We don't yet know that output is correct because the error could be in the other part. But if verifier A also comes back and says, no, everything's cool, I ran the first 100 transactions and I ended up with that interim state, there's no way that if both verifier A and B are correct, that could be an incorrect result. And so they can do those two checks in parallel or even out of order. You could check the second half before you check the first half. But that's only true once you have a candidate result, right? And so we need these powerful execution nodes to create the candidate results, but then the verifiers can, with very large parallelism, check each step, check their work in parallel. And so you then run into the verifier's dilemma, and so we have this thing that we called SPOCs, which is a specialized proof of confidential knowledge, which makes it much harder for verifiers to be lazy. It doesn't. It requires an extra piece of information for a verifier to. The critical part that we have that helps us address the verifier's dilemma is that it is not optimistic. It is not assumed that the execution node output is correct unless it is challenged. It is only accepted that the execution output is correct if a critical number of verifier nodes say that it's correct. And what's more is that because it's possible to create an objective proof of incorrectness, we don't need to count on a popularity contest, right? So if 1,000 verifiers say a result is correct, and one verifier says the result is incorrect, the consensus nodes themselves can look at that proof of incorrectness and say, nope, you were right. These 1,000 guys over here that said it was correct, they're wrong, right? And so we can slash all 1,000 of those verifiers on the proof given by a single verifier, because they have to point. They point and they say, look, I found it. I found the first state transition that was invalid. And everybody, all the consensus nodes, any client software can verify it and say, yeah, you're right. That was invalid. And so we know that those 1,000 people should slash. We know that the execution nodes that proposed that result should be slashed. And so it doesn't have to be a popularity contest. But we still have this thing called a SPOC that is an additional attestation that to a piece of data, the confidential knowledge, that comes as a side effect of computing the result. And so if I rubber stamp an execution node's result, I can't actually produce that, what we call a result approval, because the result approval requires that I make this specialized proof that I have the same confidential knowledge that is a side effect of running the VM. And it's actually, if I'm actually doing my work, it's free. Like that output is free. If I don't do the work, there's no way I can come up with that confidential knowledge. And so we use the specialized proof of confidential knowledge. And then and then it comes right back to the consensus nodes again. The consensus nodes get these result approvals, and they say, look, that 1,000 people have checked this result. And all the execution nodes agreed on this result. So the probability that this is an invalid result, an incorrect result, is astonishingly low. And so we can confirm that output with very high probability. And we call that final thing result sealing. And when a result is sealed, that actually gets included in a new block, a future block that is itself queuing up more transactions for execution. And so the whole thing comes around and connects with itself. And at the end of the day, the consensus nodes are the final arbiters of what is correct, what is valid. And they are depending on all these other nodes to do the heavy lifting, but they have all the power of what is in the chain, what is finalized, what is sealed, it rests with the consensus nodes. And so that's where all the security rests, is on those consensus nodes.
Okay, yeah, that's very cool. I'm wondering, how long does it take for in blocks for this whole process to happen, like from finalizing to sealing, and maybe like what are actually the block times kind of in flow or proposed?
Yeah, so yeah, it's tough because running internally, it's very fast, and we don't we haven't run the full system globally yet, and so our estimates are that the final block sealing will come somewhere between 5 to 10 seconds after the block is initially finalized. But the point is, the interesting point is that if there is an interim result from the execution nodes, right? So if an execution node says, hey, I have a result. It hasn't been checked by the verifiers yet, but I have a result. That is signed. And so if it's a low value transaction, or even a relatively like a moderately valuable transaction, you can trust that execution node's output with a very high degree of certainty, because if it's a signed what we call execution receipt, and producing an invalid signed execution receipt is a slashing condition. And so either that execution result is correct and you can that output is right, or that execution node and all other execution nodes that produce the same execution receipt will be slashed. And so that could represent millions of dollars. And so in the same way as in Tendermint consensus, when you say, well, either the blockchain has not forked and this is a finalized block, or a minimum of 1/3 of nodes are going to be slashed, you have the same thing with the execution result. Either this execution result is correct, or every single execution node that produced this result is going to be slashed. And so you can make that assessment yourself. You can say, well, there's $10 million staked in these execution nodes that have produced this result. And so either this result is correct or somebody's going to lose $10 million, right? And for most transactions, that's fine. You just go ahead. Even better, you could say, well, look, I happen to know who's running that execution node, right? Like because the execution nodes, there's a relatively small number of them, you can actually, in the same way that many Cosmos validators are well known, you could say, look, if I see an execution result signed by Chorus One, I'm just gonna more than them getting slashed, I just trust their reputation. And so I'm pretty happy. And if you're doing a multi-million-dollar transaction, yeah, by all means, wait the 10 seconds, right? Wait for that result to get sealed, for all the verifiers to have checked that result, and for it to be finalized in the block, or sealed into the blockchain again. But for the vast majority of transactions, once you see an execution node has produced that result, especially if you know who that execution node is being run by, you'll feel you can, with very high confidence, within a couple seconds, know what the result of your transaction is.
Okay, yeah, that sounds encouraging. I'm wondering now. You said there's $10 million staked with the execution nodes. I'm kind of, one thing I really wanted to talk about is kind of the economics behind this, or how is determined what part of stake goes to which nodes. Where's the equilibrium there? So basically, I'm assuming all these different nodes are all staked in flow tokens. Can you maybe talk a little bit about how much is staked with which nodes? Do you have like some thresholds that you set there, or how do you determine that?
Yeah. So there's an analysis that we've done internally where you look at various different kinds of attacks, right? So one attack that you could, I'll just give two examples that sort of come up already, right? One attack you can imagine is, well, I'm just going to do a forking attack, right? I don't care about these execution nodes, these verifier nodes, the collection nodes. I'm just going to attack the consensus, and I'm going to try and fork the network. Or I'm going to capture 2/3 of the nodes, and I'm going to start, publishing blocks that have whatever in them that I want, right? That's sort of one kind of attack you can imagine, right? Is to just ignore all the other nodes and attack the consensus nodes. Another example you can imagine is, well, maybe I just want to halt the network. And so I'm going to stake, I'm going to be the only staker for all execution nodes, and then I'm just not going to produce any results. And that would halt the network. Alternatively, I could get 1/3 + 1 of the consensus nodes, and I could halt the network that way, because then we can never get a 2/3 majority of people signing a block, and the network halts. And so if you look at those two attacks, you say, well, I could get all of the execution nodes and halt the network, or I could get 1/3 + 1 of the consensus nodes and I can halt the network. There's no point in making one of those attacks more expensive than the other, because a savvy attacker is just going to choose the cheaper one. And so if you can if staking all the execution nodes costs half as much as staking all of the consensus nodes, then it's much cheaper to halt the network by getting 1/3 of the consensus nodes. Whereas if the consensus nodes have 10 times as much stake than the execution nodes, then the cheapest way to halt the network is by having the execution nodes. And so we just have to balance that. We just have to say, look, the stake that goes to consensus nodes needs to be about 3 times as much as the stake that goes into execution nodes when we're concerned about the halting attack. But there's other kinds of attacks, and so we have to do that analysis across all of them. And then you end up with these it's just a big linear equation, right? And you just have to optimize that linear equation. And what you find is that that unsurprisingly, right, as the system is designed, the node type that ends up with more stake than any other node type is the consensus nodes. And so, at one level, they're the only nodes that are really staked, right? You can almost think of the other nodes, the money that they're putting up, is more a bond against Byzantine behavior, because they don't have any voting power with those locked tokens, right? So as an execution node, I may have locked up $1 million or whatever it ends up being to be an execution node. But that doesn't give me any voting power in the consensus process. If as like an organization, I want to run both, I can stake for a consensus node as well. But that the money that I've locked up to run the execution node, that's just a bond against me making me producing invalid results. And so if I never produce an invalid result, I just get paid. And if I produce an invalid result, well, then I should be slashed, because the work I'm being asked to do is fully deterministic. There's no subjectivity in the work done by execution nodes. And it's the same for verifiers, and it's similar for collection nodes, where the work they're doing is not in some definitions of the word stake, it's not, maybe you don't want to think of it as stake. I think informally, well, you can think of it as stake because most people think of stake as money you put up so that you don't, to prevent against Byzantine behavior. And that's certainly what this money is. But it's not stake in the sense that it gives you a stake-weighted vote in the consensus.
Yeah, okay. That's really helpful. I think I was also kind of looking at it more from a different perspective, I guess. Now we're talking about these attacks and the attack vectors there, but from the perspective of a staker, I basically have to choose which node type I may be running. Maybe let's say I have 100 flow tokens. Let's say I could run 2 consensus nodes or 1 execution node, but obviously with one of them, I might have like a higher return of investment or something. Maybe can you maybe, is there some way that there's some equilibrium achieved between these, or how do you think about that? So maybe it's the most valuable thing for my organization to just run these execution nodes. So I want to try and stake only those. Do the rewards then get lower so that other node types become more?
Yeah, exactly. And so running a node, we know, right? We know with certainty that running a node software has some extrinsic costs and intrinsic value. And the reason we know this with absolute certainty is because thousands of people are running Ethereum nodes but not mining, right? So there is some value that you get from running a node, right? And it could be like us, right? We ran our own nodes for a long time when we first launched Cryptokitties, right? We need to know what's happening on the blockchain, so we run our own full nodes, right? It could be somebody like Alchemy, which is a service provider that we use to run our nodes now, right? Why are they running nodes? Well, because we pay them to get that data, and we trust them to always give us the correct data, so we don't have to run our own nodes and have that additional operational cost anymore. And so we know that there is extrinsic value in running these nodes. We also know that there's extrinsic costs, right? Like we would just call those operational costs, but like you have to run a computer, you have to pay for an internet connection, right? You have to pay for the electricity. And so we have intrinsic costs, right? That's the staking cost, and intrinsic value where we pay you, right, for your services. But there's no way for the chain to estimate those off-chain, those extrinsic things. And so what we do is we just look at people's behavior, and we start by saying, look, and again, these ratios aren't finalized, but look, we want stake of let's just use my simple example from before. We want about 3 times as much money to be staked in consensus nodes as execution nodes. So what we'll do is we'll collectively pay consensus nodes 3 times as much as execution nodes, right? And then we'll see what happens, and we'll see how much gets staked in them in each one, right? And what might happen? Well, lots of people might run consensus nodes because it's a very lightweight process. We've taken a lot of effort, that you don't need a lot of bandwidth. People love the idea of participating in these networks, and so what you might see is that people are running lots of consensus nodes compared to what you might expect from the financial return, because the extrinsic reward of being a part of this network is valuable to people, right? Which I think represents a lot of Ethereum nodes. People run Ethereum nodes because they just want to be a part of it, and they want to be able to. They want to know that they're contributing to the security of the network. And so what we'll do is, if we see that imbalance where more people are running consensus nodes than execution nodes, that the total stake in consensus nodes is more than 3 times the stake in execution nodes, then we'll just start edging up what we're paying execution nodes. We'll say, well, look, clearly there is some extrinsic factor here. Maybe it's cost, maybe it's value, but that we need to give execution nodes a little bit more money so that they stake more, and redress this imbalance. And so it changes very little each epoch. I think we're imagining about 1% per epoch it'll change, but over time it should equalize. And as things change, as suddenly running an execution node becomes very lucrative because lots of people want to pay you to get that data fresh and fast without having to wait for the verifiers to go through it. Then suddenly we may see that balance go the other way, and this system can find that equilibrium that result from the market pressures. Okay,
yeah, that's a nice system, and I think it would be really interesting to see this in practice, how this would work, and also be part of this decision-making process kind of ourselves if we would validate on flow. I think it's really interesting to think about that. Yeah, so maybe I think we've already been talking for like 50 minutes. Maybe just like one final question to wrap up is maybe what's the current state of Flow? When is there going to be like some testnet that people can play around with, or what are like resources you would recommend for people that are interested to get to learn more about Flow?
So I think you can get a really good taste of what developing on Flow is gonna feel like by going to playground.onflow.org. And that is a live version of the emulator running right now where people can go, and we've got a bunch of examples set up there, but you can put in any code you want. It's an early version of Cadence. The syntax is not finalized. Some of the features are missing, but it lets you write smart contracts using the resource-oriented programming, which is a new feature that, sort of the first being exposed in a high-level language with Cadence. And it's sort of the defining feature of the Move language that the Libre team has. And so you can play with that, and you can get a taste of what it's like to submit transactions and smart contracts in this new language. The second thing that people who want to start thinking about building on top of Flow, I recommend that they sign up for our alpha program. So there's a number of app developers that we'll be working with, giving them early access to the emulator and whatnot, but more importantly, giving them direct support so that as they're building their dApps, they can talk to our team and in some cases help shape what that's looking like. The first version of the Node software is going to be shared with our partners next month. And so the people who will sort of be the initial validators will start to be able to test that locally. And then we anticipate that around that time we should have at least some potentially gated access to a testnet. But hopefully we'll be able to open that up over time. And then in the May-June timeframe, we want to start having what we're calling the beta mainnet, which will have live customer data on it, will be run by our initial validator partners, but which will have several training wheels on it. So we won't allow arbitrary smart contracts to be uploaded. We'll want to approve the smart contracts. The validators will be the people who are holding the token today, and those people have lockups, and so we'll know who the validators are, and we'll have direct relationship with all the node operators, and so we'll be able to be resistant to we'll be able to use sort of social mechanisms to be resistant to certain kinds of attacks that the code might not be hardened against yet. And then later in this year is when we imagine to be able to take those protections off and allow sort of general unrestricted access to the network. Okay,
cool. Yeah, that's pretty helpful. I will link to all these pages you mentioned in the show notes, and looking forward to see it live and what people will build with Flow. Thank you so much for coming on, and to our listeners, make sure to visit all these sites if you're interested in Flow, and check out the many white papers and primer if Dieter's explanation wasn't good enough today.
Well, I appreciate the chance to come on and talk to you today, Felix. It was a lot of fun.
Okay, cool.
Thank you for listening to the Chorus One podcast. Visit chorus.one for more information about our work. Don't forget to subscribe to the podcast to stay tuned on new episodes airing every Monday.